Dark matter is one of the most mysterious and fundamental components of the universe, constituting an estimated 27% of the cosmic mass energy budget. Despite its invisible nature, the presence of dark matter is inferred through its gravitational effects on visible matter, radiation, and the large-scale structure of the universe. This video explores the history, observations, and theoretical developments that led to the discovery of dark matter, tracing its journey from early astronomical anomalies to the forefront of modern cosmology. The first clues hinting at the existence of unseen matter emerged in the early 20th century. Dutch astronomer Jacobus Kapteyn suggested that unseen mass might be influencing stellar motions in the Milky Way. Around the same time, British physicist James Jeans also speculated about the presence of dark matter in the universe. However, it was Swiss astronomer Fritz Zwicky who made the first compelling case for dark matter in the 1930s. While studying the Coma cluster of galaxies, Zwicky measured the velocities of galaxies within the cluster and found that they were moving much faster than expected, based on the visible mass alone. Using the virial theorem, he calculated that the total mass of the cluster needed to be much greater than what was observable in stars and gas. Zwicky termed this unseen component dunkle materie, or dark matter, suggesting that an invisible mass was exerting gravitational influence. While Zwicky's findings were largely overlooked at the time, more substantial evidence for dark matter emerged in the 1970s through the work of astronomer Vera Rubin and her colleague Kent Ford. Rubin studied the rotation curves of spiral galaxies, specifically measuring the velocities of stars at different distances from the galactic center. According to Newtonian mechanics, stars farther from the center should exhibit declining orbital velocities, similar to how planets in the solar system move more slowly as their distance from the sun increases. Contrary to this expectation, Rubin found that the outer regions of galaxies rotated at nearly constant speeds, indicating that the mass of the galaxy was not concentrated at the center, but was instead distributed in an extended halo. These findings could only be explained if a significant amount of unseen matter was present, exerting additional gravitational force. Rubin's work provided strong observational support for the existence of dark matter, convincing the broader scientific community. Further evidence for dark matter came from studies of the cosmic microwave background, CMB, the faint radiation left over from the Big Bang. The CMB provides a snapshot of the early universe, revealing fluctuations in temperature that correspond to regions of varying density. Precise measurements of these fluctuations, particularly by the Wilkinson Microwave Anisotropy Probe, and later the Planck satellite, allowed cosmologists to determine the composition of the universe. By analyzing the power spectrum of the CMB, scientists found that the observed distribution of temperature fluctuations could only be explained if most of the matter in the universe was non-luminous and did not interact with electromagnetic radiation, properties characteristic of dark matter. The findings confirmed that only about 5% of the universe consists of ordinary, baryonic matter, with dark matter and dark energy making up the rest. Gravitational lensing, a phenomenon predicted by Einstein's general theory of relativity, provided another method to detect dark matter. When light from distant galaxies passes through a massive object, such as a galaxy cluster, its path is bent due to the gravitational influence of the intervening mass. This effect, known as gravitational lensing, allows astronomers to infer the distribution of mass in the foreground object. Observations from telescopes such as the Hubble Space Telescope and the Subaru Telescope have mapped the distribution of dark matter by analyzing lensing effects. One of the most significant studies in this area was the Bullet Cluster observation, where two galaxy clusters collided, separating the visible matter from the bulk of the total mass. By examining the gravitational lensing patterns, researchers demonstrated that most of the mass resided in a dark component, strengthening the case for dark matter's existence. The nature of dark matter remains one of the biggest unsolved mysteries in physics. Various theoretical models propose different candidates for dark matter, with weakly interacting massive particles, WIMPs, and axions being the most prominent. WIMPs are hypothetical particles that interact only through gravity and the weak nuclear force, making them difficult to detect. Numerous underground laboratories, including experiments like LUX, Xenon, and Pandax, have been searching for WIMPs by looking for rare interactions between dark matter and ordinary matter. However, no definitive detection has been made. Axions, another dark matter candidate, are light, hypothetical particles proposed to solve problems in quantum chromodynamics, QCD. Experimental searches for axions include the Axion Dark Matter Experiment, ADMX, and other precision measurements, but their existence remains unconfirmed. Although dark matter is the leading explanation for the observed phenomena, alternative theories have been proposed. One of the most well-known alternatives is modified Newtonian dynamics, MOND, which suggests that gravity behaves differently at very low accelerations, potentially negating the need for dark matter. Another alternative is modified gravity, MOG, which modifies general relativity to explain galaxy rotation curves and cosmic structure formation without dark matter. While these alternative models provide some explanations for specific observations, they struggle to account for all the evidence supporting dark matter, such as the CMB fluctuations and gravitational lensing data. As a result, most scientists continue to support the dark matter hypothesis. The search for dark matter remains an active and evolving field in cosmology and particle physics. Future experiments, including next-generation direct detection experiments, high-energy particle colliders, and advanced space telescopes, may provide further insights into the nature of dark matter. Projects such as the Vera C. Rubin Observatory and the European Space Agency's Euclid mission aim to map dark matter distributions with unprecedented precision. Understanding dark matter is crucial not only for cosmology but also for fundamental physics. Whether through direct detection, indirect observations, or new theoretical breakthroughs, solving the mystery of dark matter will reshape our understanding of the universe and its fundamental forces. Until then, dark matter remains one of the greatest enigmas in modern science, lurking in the cosmos unseen but undeniably influential.